Welcome. My name is Wouter Pieters. I'm from Groningen University. That's where I hold the chair of Atmospheric Composition Modeling, part of the Energy Academy Europe in Groningen, one of the large initiatives, also under the top sector of energy. I also have an affiliation with Wageningen University. Actually, this morning I only had to drive from Wageningen up here because that's where I live and where I have most of my current position. So I want to thank the organizers, of course, for inviting me and giving me a chance to speak to you today. An audience which is not typical for me in the sense that I tend to speak to people from my field, of course, when I go to large international conferences, people that have a background in meteorology or in climate science or in carbon cycle science, isotopes, for instance. That also made it a bit difficult. What am I going to speak about today? Luckily, I had some guidance by the title, although greenhouse gases, emissions, and the carbon balance is too big of a chunk to chew off in 45 minutes. So I'm kind of going to focus on a few key items. One of the items that I'm going to focus on is on CO2 in the atmosphere, which means that I'm going to leave some of the other greenhouse gases, methane, for instance, nitrous oxide, and also SF6, sulfur hexafluoride, to the side for now. So we'll focus on carbon dioxide also, because that's, of course, the gas that we've heard mentioned the most times already today, even though we've had one talk so far. Carbon dioxide, 450 ppm. These terms mean something to everybody in this audience, I'm sure. We heard this morning also from the rector saying, well, there's a lot of need to separate fact from fiction. And I think that's nowhere more true than in the field of greenhouse gases and CO2. It's very easy to go from CO2 to greenhouse gas forcing, and from greenhouse gas forcing, climate change comes on the table, and then we're talking about sea level rise, and we're talking about dikes, and we're talking about very scary things that people have a belief on. Whether you think it's going to happen or not is an important topic. And it's being polarized a lot, because there's a lot of information out there which is not completely accurate for some reason. Different parties are blaming each other. Disinformation is being spread by either the companies that have invested in the energy infrastructure or by the scientists that want to have funding to research this. Of course, we know that this is not going to lead anywhere. This is not going to lead to the kind of collaboration that we need to actually tackle the problem. So what I'll try to do today is kind of stick to some of the basic facts. It's not going to be a talk about climate change. It's not going to be about how scared should we be of CO2. I'll try to give you some basic facts about CO2, greenhouse gas forcing, simply based on a bit of physics, a bit of chemistry, and a bit of mathematics. There's actually going to be a few differential equations in this talk, which is not to scare you, because there's also a bunch of Wikipedia figures, and I'll kind of go through, and I'll come back up a few times, and I'll make sure that everybody can follow this. So where do we start? We start with the Mauna Loa CO2 record. Everybody has seen this. If you hadn't seen it in your professional work, you've seen it in the movie Inconvenient Truth by Al Gore, who's actually also on, well, next to a very large screen like this, and he has a stage jack, and then he goes all the way and he says, oh, CO2 goes up and up and up and up and up. And of course, this really scares people a lot. This figure is going to come back multiple times in this talk. Why? Because it really is the basis for a lot of the scientific work that is happening in my field. Of course, there's immediately clear that CO2 is going up, and we all know that this is fossil fuel related. Although I'll show you some evidence that actually helped us realize or even quantify that this is fossil fuel CO2 related. There's a lot of other interesting things going on in this curve, but I'll come back to that during the talk a few times. This curve was in the news, of course, in April 2013, when carbon dioxide passes a symbolic mark, which I think is a very appropriate title. It passed the 400 ppm mark, which, of course, is symbolic, because the day before it was 399, and the day after it's 401, and nothing really changed. So typically you go onto the web, onto the internet, and you kind of look for, okay, so what's the reaction to passing this symbolic mark? Well, a lot of news items, serious news items, but of course also, what does the world look like with 400 ppm? Well, what data says it looks like is actually kind of funny, because it says current reading 399.5, which is it's sort of a quip, because even though we measured 400 ppm that day, during a few hours of the day, and these were measurements that were deemed good. We didn't think there was anything wrong with the instrument or wrong with the flow. There wasn't anybody smoking a cigarette next to the inlet or something like that. They were good measurements of 400 ppm. But if you averaged it to all the day, it actually turned out to be only 399.5. But they had this press release ready, of course. They were waiting for the day that this was going to happen, so they released it. April 2013, Mauna Loa reading was 400 ppm. So of course skeptics say like, oh well, whatever, nothing happens. Al Gore says, be scared. Plan says, yay, great, the more CO2, the better for us. And then of course there's another view here is what it really looks like. It's just a number. So what I want to show you a little bit is why should we care about X 100 ppm? So what? 100, 200, 300, 400, 5, 6, 7, 8. Do we really need to care? This figure kind of shows you that we haven't seen, well, we've only seen, let's put it like that, a few numbers for this X 100. We've seen 200 and we've seen 300. And with we, I mean modern man. Estimated about 200,000 years ago is when Homo sapiens, the species that we all belong to, started to develop seriously. Of course, we have a longer history of other people that lived on the earth, basically. But none of those people experienced 400 ppm. So it's kind of novel. For that reason alone, it's interesting to care about 400 ppm. We are going to live in an era where CO2 is higher than ever before. Should we then be scared? Is this a reason to worry? No, not per se. We know that CO2 is tied to temperature. And so, of course, from here, it's very easy to go to climate and say, like, ooh, it'll be warmer than ever before, which is indeed what we currently think is going to happen. Then again, the variations that we're seeing of a few degrees that we also are predicting for the next 50 years are not that special in the past 200,000 years. Of course, it is interesting to realize that the periods of this record when it was colder, we had a world that was glaciated all the way up to about Wageningen, where I live. Yeah? So the world did look a lot different when it was colder. But what I don't want to do is go from here straight to climate change and say we need to worry about CO2 because temperatures will rise. What's important to realize about CO2 is that it's a gas in the atmosphere which has a very well-known climate forcing. Yeah? So now we're talking about physics. Physics that is about 150 years old, I would say. Late 19th century, already John Tyndall did some research on greenhouse gases and how the absorption of infrared radiation works. Later picked up by Svante Arrhenius, who was the first one to postulate that if CO2 increases, he was referring to carbonic acid because that's what he used in his experiments, in geometric progression, so that means if you multiply it with a constant factor, the augmentation of the temperature will increase nearly in arithmetic progression, which means with a fixed number. Yeah? So if you double CO2, a few degrees extra. If you double it again, another times that few degrees extra. Very basic physics. This was not based on climate yet. What I say is we need to think about climate forcing and not directly about climate change. It's because climate forcing, you can kind of see it as the thermostat of the atmosphere. When you increase CO2 in the atmosphere, you are turning the dial on the thermostat. We know that extra heat is going to be trapped in our atmosphere. Yeah? Just like when you turn on your thermostat, you turn it up in your house, you know that your energy system is going to work and your central heating system is going to put heat into your house. So in a closed system, like these guys were studying, the temperature will go up. That's a logical reasoning if you turn off the thermostat. But of course, climate is not a closed system. There are other actors in the climate system. We know, for instance, aerosols that have a cooling effect. We know vegetation that can respond to temperature. We know that the oceans have a large heat capacity. So even though we might know that we're putting on extra climate forcing, it doesn't necessarily say that temperatures are going to go sky high. Yeah? And that's why I always tell people, please separate climate change from climate forcing, because climate forcing is a physical principle that we really understand for more than 150 years. Climate change is a very polarizing topic of which we know something, but definitely not everything. Don't bring in everything when you're studying CO2. Climate forcing alone is enough reason to care about 300, 400, 500, or 600 ppm of CO2. There's a better reason. If we want to steer completely away from greenhouse gas forcing and we want to steer completely away from climate change, because that's not leading us to better collaboration, think about the oceans. We know from chemical principles very well what happens to CO2 if it dissolves in water. It causes acidification of the ocean. And this is actually what we currently have measured and constructed with computers about what the pH of sea surface, the ocean surface, is changing in the past 100 years. And there's a change of 0.1. Points of pH. pH is a logarithmic scale, just like the Richter scale that we know for earthquakes, a logarithmic scale. So that means there's been a 30% increase in H plus ions. Do people remember? P minus logarithm of H plus gives you the pH. This is high school chemistry. Yeah? I hate it when professors say, oh, this is high school chemistry, because it's usually something very complicated that you don't understand. But in this case, it's true, I think. This is high school chemistry. So what happens is we have this CO2 in gaseous form going into the ocean. It makes a complex of carbonate and bicarbonate, and in the process we have these H plus ions produced. 30% more of this gives 0.1 drop in the sea surface of the ocean. So this is basic. This is quite simple. So why do we worry about the pH of the oceans? It's because when we have more H plus going into the ocean, the way to neutralize it is by adding more of this carbonate, CO3 2 minus. And the source of this is calcium carbonate. There's a lot of calcium carbonate in the ocean, and the ocean is a very large reservoir, and we can easily store decades of fossil fuel emissions in the ocean, given its volume and the amount of calcium carbonate. So in principle, there's nothing to worry about. The problem is that the reachable part of the ocean is only small. The surface ocean itself is only a couple 100 meters thick. So it has to go first into the surface ocean. It sticks around there for a long time before it can go into the deep ocean. Yeah? And in the deep ocean, in the end, we can neutralize that extra CO2, or actually the extra H+. Yeah? There's no problem about that. But before it reaches the deep ocean, it'll spend years and years and years, actually multiple decades, in the surface ocean, which is only a small reservoir. And if we have calcium carbonate in the surface ocean, it's in the form of calcite and aragonite, two forms that easily dissolve if there is a lot of H+ around. And it happens to be that most of that calcium carbonate is in living organisms. So this is why coral is being attacked by CO2, or actually H+, by increased acidity of the ocean. What I want to say about this is that we know that this is happening. We can see the drop in pH. We know why that's happening, because we're pumping more and more CO2 to the surface ocean. And again, there is no scientific question about this. Yeah? Of course, what is going to happen to these animals? How long is that CO2 going to be around? What will it do to fish, to biodiversity? These are the much more difficult questions that we cannot answer right now. The chemical principle of dissolving CO2 in water to make an acid is very, very easy. As a matter of fact, you can go home tonight, you can take a glass of regular water, and you can take a glass of sparkling water, which is water with CO2 dissolved in it, and then if you have some seashells, put it in both, and look the next day. Yeah? What's happening to your seashell in your glass of sparkling water, spaarrood, is exactly the same process that you'll see going on here. High school chemistry. Just a short introduction about why do we care about X 100 ppm CO2. And I hope that you agree with me that I've steered away from climate change and climate science and climate skeptics for now. The next question that I want to answer is, what do we know about the carbon balance currently? And what do we know about the contributors to CO2 increase? After that, I'll talk a bit about integrated greenhouse gas monitoring. And I also want to get to the question, how fast are we approaching dangerous levels? Which was sort of a sub-question given to me together with the assignment to speak to you, so I definitely want to try and go in there. So at some point in the presentation, I might hurry up a little bit or even skip a few slides to make sure that we get to that final topic. So back to the Mauna Loa CO2 record. Like I said, there's a lot more other interesting things going on in this record than just the long-term increase in CO2. For instance, we can see that CO2 is not increasing every year at the same pace. We can also see that in addition to the increase, which is shown in black here, there's a seasonal cycle in red, which we know is the biosphere, which in summer turns green. All the CO2 is on the leaves and on the trees. And then in fall, when the leaves fall and the twigs fall, this CO2 is returned to the atmosphere. So there's this long-term modulation. Except what we see is that every year, at the end of the year, CO2 is a little bit higher than what we started with the last year. So every year so far has been a new record in annual mean CO2 since the time that we started measuring this, which is also quite interesting. So these signals we try to understand in my field. We try to interpret this graph with the view of what are all these wiggles? Why is not every year the same? Why is it increasing more fast one year than another year? And why is the amplitude of this seasonal change not the same every year as well? Yeah? So really try to pick apart this time series into different components. Well, the easiest thing to do is to say, okay, let's go for this long-term mean again. And then we can say we've increased CO2 about 50 parts per million over the past 30 years. And then we can say, all right, let's make this quantitative a little bit. And we'll use our first differential equation. Well, it's a baby differential equation. It's not really, doesn't really count. But on the left-hand side, you can see there's delta CO2 over delta T. So we have the differential of two quantities. So the change in time of CO2 must equal the F, which is fluxes of fossil fuels, fires, ocean, and biosphere, which are just 4 terms that I've dubbed so far. We could use other terms in here as well, but these are the main actors in the CO2 balance. You'll notice, for instance, that volcanoes is not on this slide because the flux of CO2 from volcanoes is really, really small compared to these other 4 actors. Yeah? Kind of debunking some commonly misperceptions where people say, oh, but it's all about volcanoes. I even saw people say, like, well, Mauna Loa is a volcano, so actually you're not measuring CO2 from anywhere except from the volcano. It's not true. So if we know that CO2 is nearly inert in the atmosphere, there's no way that it's being removed except by exchange with the other reservoirs, we can do a little calculation. Typically, CO2 is reported in emissions of petagrams of carbon, 10 to the 15th grams. We know that if a petagram carbon comes into the atmosphere and it mixes completely through the volume of the atmosphere, it changes CO2 by about half a ppm. So that means if we see 1 ppm increase in the atmosphere of CO2, there must have been 2.1 petagrams of carbon released into the atmosphere. Or if we see a decrease of 1 ppm, of course, that goes the other way around. So with these numbers, we can do our first little bit of math, and we can say, all right, we had 395 ppm this year, 342 ppm 30 years ago. We convert it from ppms to petagrams by using this factor here, and then we get to, all right, there's an increase of 3.8 petagrams carbon per year over the last 30 years. If I then fill in numbers for what we think the fossil fuel emissions are, which we know pretty well based on economic statistics, production data, and things like that, we also make an estimate of how much the fires is. This is mostly land use change. There's a big component there of land use change where people are converting forests to arable lands, for instance, to grow palm oil. We have already 2 terms on the right-hand side filled, and we can do a simple mass balance to say the sum of ocean and biosphere must equal minus 3.8, negative. In other words, the global ocean and biosphere are a sink of carbon dioxide. Yeah? Because of the 8 petagrams that we're putting into the atmosphere, we're only seeing 3.8 remain in the atmosphere. So 4.2 by balance must have been removed by ocean and biosphere. So it's a pretty simple thing. I think everybody knows kind of from science, from reading, that there must be sinks of carbon dioxide and that it's only about half that remains in the atmosphere. But actually doing it from the graph with the numbers, I think, is always kind of illustrative, because this principle will expand upon later in my talk as well. It's simple. You say, all right, ocean and biosphere together are a sink. But now come the real questions. Why are these sinks? How large is ocean relative to biosphere? Where are these sinks? Are these sinks constant? Or are they changing over time? Can we depend on these sinks to remain for another 50 years? And if we increase fossil fuel emissions and CO2 in the atmosphere, will these sinks increase as well? Well, that, of course, is the field of science that I work in, which sparks a whole lot of papers in Nature and Science and other journals to figure out how is this system working. Part of that question also is, how accurate is that number of 6 petagrams carbon over the last 30 years? Do we know these fossil fuel emissions as well as we think we know them? Can we put them in the balance like this and then solve for the other terms? So let's go back to the CO2 record now. And then I want to talk a little bit about this term of the fossil fuel emissions. After all, we're talking here about Energydays, energy-related CO2 in the atmosphere. I've just said that of the about 6 petagrams of emissions that we put in over the last 30 years, about half of it remains. How do we know this half? Why did I put in this 6? And do these numbers really work out? Well, we know, of course, from statistics that the total number global must be around 6. 6 plus or minus a half is a reasonable estimate. 6 plus or minus 0.2 is what other people say that work in the field and think they have a really good handle on these data. But typically, for any given year, there's some uncertainty on that number. But how do we know this is responsible for this CO2 increase? And it wasn't actually the biosphere or the oceans that were causing this increase, and the fossil fuels were taking it up. I'm now making it up, of course, though. One of the pieces of evidence, and this is about monitoring of the atmosphere, comes from another gas. And that gas is oxygen. Oxygen is about 20% of the air that we breathe. That's the case all over the world. It's pretty well mixed. And it changes, of course, when the column of air gets thicker or thinner, so it changes with pressure. But if you ratio it to nitrogen, which we have about 79% in our atmosphere, that ratio is really, really constant. Yeah? It is so constant that in order to see these sort of variations in the ratio of oxygen to nitrogen, you need to measure in units of per meg. So this is 1/1,000,000th of a difference from a known quantity. So you have a number that you know, you measure a sample, and then there's a 1,000,000th difference between them, and this is what is shown here. Yeah. So if you measure in the atmosphere what this oxygen-nitrogen ratio is doing, you can see that there's a curve kind of like the Mauna Loa CO2 curve, but it's mirrored. Yeah? It's mirrored because it's going down, and it's mirrored because the peaks and the troughs are at different times. Well, the peaks and the troughs are quite easy to explain, because what happens is that we have photosynthesis going on in the spring and in the summer. We saw that the CO2 is going to go into biomass, into leaves, and into trees, and this produces oxygen. Yeah? This is a very well-known process. Photosynthesis produces oxygen. As a matter of fact, the 20% of oxygen in our atmosphere was produced through photosynthesis. Yeah? So the peaks and the troughs are easy. They just correspond to CO2 being either in the biosphere or in the atmosphere. And then the long-term decline, if you look at the size of that long-term decline and how fast it's going, corresponds very well to the burning of hydrocarbons. Hydrocarbons of about 1.4 in global average consistency, so that means there's 1.4 hydrogen for every carbon molecule in the mix of fuel that you are burning. And burning is an oxidation reaction, so it's just adding O2 to this fuel. And if you work out the balance, then you can see that for every mole of fuel burned, we lose oxygen and we produce CO2. So the rate at which oxygen is declining corresponds very well to the rate at which we're burning fossil fuels. So this is sort of independent evidence that we can use. Another piece of independent evidence comes from isotopes. So typical CO2 consists of carbon-12 together with oxygen. Actually, most of the carbon around us is carbon-12. Only 1% of it is carbon-13. Yeah? So 1% of all the carbon in the world is carbon-13. But if you look at where that carbon-13 is located, you can again see something very similar to the oxygen. There's a long-term drawdown. This is a shorter window, yeah? So it's not as easy to see. And there's this big seasonal cycle. Well, the seasonal cycle, I won't go into the details, is again related to this very large change in the atmospheric reservoir of CO2 with the seasons. The long-term drawdown means that we need something going into the atmosphere that is typically light carbon, yeah? So that has relatively a lot of carbon-12 in it. That source of carbon, the only source of carbon that we currently know to be emitted in sufficient quantities to give this drawdown, is fossil fuel burning. Yeah? Fossil fuels are basically old plant material. So when the CO2 in the plants is at this low value of about -30, then you emit something with a signature of -30. Minus is a bit of a strange scale here, but imagine that you need something that is really here on the scale to make this long drawdown. That here on the scale is fossil fuel emissions. So carbon-13, like oxygen, is an independent way that we know that fossil fuels must be responsible for the long-term drawdown. Another really interesting one is the carbon-14 isotope. And just so that people remember what carbon-14 is, this is called radiocarbon. Radiocarbon we use to date stuff. Yeah? When we find a mammoth in the peat grounds in Siberia, or sometimes even in the Netherlands, we find artifacts or bones in the peatlands. We do radiocarbon dating to figure out how old is this stuff. Yeah? So carbon-14 is used to figure out how old is something. You can go back about 60,000 years with radiocarbon dating. After that, carbon-14 has decayed out of the samples, and you measure nothing anymore. So it doesn't have any carbon-14 anymore. And it just happens to be so that there is one thing in our atmosphere which is really, really old, fossil fuels. Fossil fuels have been underground so long, it no longer has any carbon-14 in it. So if you burn it, you see something in the atmosphere that looks very, very old. And this is what we're seeing, is that there's a negative trend of this carbon-14, which means that we are putting something in our atmosphere which is very, very old, and we're putting more and more of it in. So it needs a strong source of old carbon. Well, this old carbon is the fossil carbon that we are burning. So carbon-13, carbon-14, and oxygen together are giving us kind of a fingerprint of the fossil fuel emissions. A fingerprint that doesn't just work out the way I'm speaking now, but it works out quantitatively as well. You can do that same mass balance equation for these gases and figure out that these numbers are what they are. And this brings me to the topic of multi-tracer monitoring. I've just already told you about carbon dioxide. This morning we've heard already about clean burning of power plants, so that means that there's relatively little CO being produced for every CO2 molecule, so the CO2-CO ratio is very high. It means that different activities related to energy use, related to fossil fuel emissions, have different fingerprints in all these different gases. And I've just given 4 here, but it's actually, the list can go on. You can put NOx in here, you can put sulfur in here, you can put vanadium in here, which is also a part of fuels, for instance. Propane, ethane, benzene, toluene, all these gases are part of fossil fuel emissions, and all of them identify some sort of form of burning for you. So just as an example, I already told you the power plant we can recognize because oxygen goes down, we're burning. Carbon-14 is old, typically the fuel there is quite old. Carbon-13 goes down because it's very light, and the CO2-CO ratio is quite high. It's clean burning because the power plants are very efficient. This is much different, for instance, when we're burning wood, or when we're adding biofuel to the mix. Yeah? This makes a different ratio of these gases. The carbon capture sequestration is also interesting, because this is something that we do want to monitor from the atmosphere. We do want to help people understand that this can be done safely, and we want to tell them from minute to minute that this is safe. How can we do it? We monitor these gases, and then in oxygen, nitrogen, we'll see something interesting. Because if there's a leak, we'll see CO2 coming out in large quantities, which is really old, but we won't see a drop in oxygen. Why not? Because that CO2 wasn't burned recently. It's just CO2 that was stored. Yeah? So this is a very telltale fingerprint of a CCS leak, is oxygen, nitrogen versus carbon dioxide. So the example that I've given is kind of on the really large scale. That's on the global scale. What do we know about global emissions, global change? But you can imagine that there's ways to do this using many more measurements and more sophisticated methods than just drawing the numbers on the board. And we call this integrated greenhouse gas monitoring. Integrated monitoring is saying, like, well, we're not just going to measure this at the top of one volcano, Mauna Loa. We're going to measure these gases in a network. And that network here that I'm showing is global. This is the global network currently. It consists of a lot of locations where people are filling flasks and sending them to a central laboratory, either in Europe or in the United States, to get measured. Yeah? So they know how much of each of these gases was in all of these places. In other places, we now have continuous instruments. So they're just measuring CO2. Air is flowing through these instruments, CO2, but also other traces are being measured. These are the green dots. Then we have aircraft going up into the air and taking samples for us. These are the yellow triangles. And then every time that we can get some money from a science foundation, for instance, we try to have campaigns as well. The one that I've plotted in here is a really interesting one. It's called the Hyper Pole-to-Pole campaign. And what they did, this was done by a professor in Harvard, is they actually went from pole to pole with an aircraft, and they went up, and then they flew a bit, and they went down, and they went up, and they went down, up and down. So they kind of made a whole curtain of the CO2 and all the other gases from one pole to another, really giving us an unprecedented look in the structure of the CO2 in the atmosphere and what the different gases look like at different latitudes at different times of the year. Being an operator on one of these flights, I talked to the guy who did this. He said, I'm never doing it again. You go crazy, because it's like an airplane that is constantly taking off and landing, and then about 50 times on a stretch of several thousand kilometers. So, great campaign. This is the longest and last equation that I'll show you. Because the idea is that if you have a network of measurements of CO2 and other gases, you cannot just do this mass balance for one location. You can do the mass balance for many, many different locations, X, Y, Z. And you can do a mass balance in time. How are things changing? So you know how CO2 is changing from one place to another. And by that, you can estimate different terms of the carbon balance, also spatially. You can say how much are the emissions from North America versus Europe. And if you have multiple gases, you can say how much are the emissions from traffic versus power plants. So we can try to pull apart this mass balance into many, many more terms and make them spatially distributed and temporally distributed. Of course, this is not something that we're doing by hand anymore. Once we're talking about this sort of exercise, we are talking about supercomputers that are keeping track of atmospheric transport. So the weather model is an integral part of this type of system. But we also have very complex models to simulate photosynthesis, uptake by rivers and oceans. The North Sea, for instance, would be part of this budget to figure out what is carbon dioxide doing there. So this sort of exercise is supercomputing with lots of bells and whistles on it. This equation is not really lively, so I'll show a few examples, which are actually examples from the type of work that we are doing. Example one that I want to show you is Carbon Tracker. Carbon Tracker is the system that I built when I was, first of all, working in the United States, and then later on when I came to Europe, I built a similar system for Europe. Carbon Tracker is a global monitoring, integrated monitoring system that is meant to take all these measurements and learn about natural carbon sources and sinks. Where are these sinks? How are they changing over the past decade? These are the main two questions that we want to address with Carbon Tracker. So we take an atmospheric transport model, because we want to know what is CO2 in all these different places in the world. We discretize the world into little boxes, with a little extra small boxes over Europe, because that's where we have a lot of measurements and a lot of interest, of course, in the fossil fuel emissions. And we simulate the transport of CO2. Actually, this is a spinning globe that's on the website of Carbon Tracker. In the PDF, it won't spin for you. But the idea is that you're looking here at a particular time frame of the CO2 distribution. So it's like a snapshot of CO2 right now, probably a couple of years ago. And you can see that there's patches with very low CO2, there's patches with high CO2, there's also the structures in these. And these are weather structures. These are like fronts in the weather system, low and high pressure systems, and they are transporting this CO2 around the world. The signature of CO2 that is emitted over New York will be over the Netherlands or someplace in Europe 3 to 4 days later. Yeah? And since CO2 is conserved in the atmosphere, we can use the weather model to back calculate what the emissions from an area in the United States must have been if we measure on sufficient locations over the Atlantic, in Europe, and on its way that is traveling to Europe. So that's the idea of Carbon Tracker. You use the transport model, you use the observations, and you back calculate what the terms of the carbon balance must have been. This is a CO2 record from Cabau, the Netherlands, one of the monitoring sites that we have in the Netherlands, where the CO2 measurements are happening just the same way they are happening on Mauna Loa. We didn't send out an email message when we hit 400 ppm, because it's years ago that we've measured 400 ppm at Cabau, because it's in the middle of a very densely populated area with lots of fossil fuel emissions. So measuring 400 ppm in that location is easy. That's what you see here also, that the variations here are much larger. And actually, well, there's already a point of 500 ppm there. The world didn't stop, but we did measure 500 ppm at Cabau. So what we do is we take these measurements and we take the model. The measurements here are in black. The model is in blue. And we make the model follow the measurements exactly by changing the patterns of emissions and uptake of CO2 from natural sources and sinks. So it's kind of like a paint-by-number exercise. If we're sitting on this Cabau tower and the wind comes from the southeast, it comes over Rotterdam in the Maasvlakte. Yeah? And we can see that CO2 will typically be high then, because we have high fossil fuel emissions. But if it's not quite as high as we thought, it might be because on its way to traveling there's a sink of carbon dioxide somewhere in the Groene Hart. Yeah? So that way we can already put a small sink in the Groene Hart. If the wind then travels from the east, and it comes from Germany, and we suddenly see that the air is very clean and there's very low CO2 in summer, it's probably because it's traveled over forested areas. Yeah? And we're not creating these hypotheses, the computer is doing this for us. So the computer is saying the most likely pattern of sources and sinks to come up with this much CO2 at Cabau is a certain pattern, which is on the next slide. So here's for a whole year after we've done that exercise with all these measurements, not just from Cabau in the Netherlands, but from this network around Europe. This is what we think that the natural sources and sinks are. Blue, reddish colors here signify that there's a source of carbon dioxide, and the blue colors are typically sinks of carbon dioxide. So most of Western Europe, even the natural part of the carbon balance, is a small positive source. Small compared to the fossil fuels, which I've not put in here. If you look at the balance from year to year, European carbon balance is dominated by fossil fuels, a little bit of an offset, about 10% by natural sinks, which is mostly in forested regions. Grasslands and crops are not contributing much to the net uptake of CO2. The oceans here are only a small term because the North Sea is a relatively shallow reservoir. Fires, we also don't have to worry about too much. If you would do this budget for Africa, the fossil fuels would be really small, the fires would be really large, the natural sinks would equally be quite large, and the ocean there is a large source in the tropics. So this balance changes from whatever region you're looking at. You can also see that it changes in time. The lowest natural uptake was in the year 2003, when we had a huge heat wave hit Western Europe. Yeah? In France, there were a lot of mortalities. I think over 10,000 people died prematurely due to the stress from the heat. This was one of the worst years for crop yields, for instance, also. So food production was low in the year with the heat wave. Keep this in mind, because the droughts will come back towards the end of the presentation. Is this concept clear? Am I moving at the right pace here? Do people understand how we can paint by numbers the different parts of the landscape to get to these maps? Because the next example that I have is a really interesting project which is still ongoing with one of my students. And this is more targeted towards the Netherlands. Yeah? And here we are trying now to go after the fossil fuel emissions. So this is not so much about the natural sources and sinks, but can we find a way to verify the reported fossil fuel emissions from the Netherlands? And we're using in this project the carbon-14, the radiocarbon. The idea being that if we have power plants or industrial activity or traffic or any burning of fossil fuels, there will be CO2 going into the atmosphere, 12 CO2, but not 14 CO2. So there's a dilution of the normal CO2, 14 CO2 ratio. You're only bringing in one of the two flavors. Yeah? The transport is then bringing this all over the Netherlands. And then when we have corn growing in the summer season, in the growing season, this ratio of CO2, 12 CO2 to 14 CO2, is recorded in the biomass that is being grown. In other words, if you go into the field in the Netherlands and you pick a cob of corn and you put it in Groningen on our instrument to measure the carbon-14, it looks like food for this mammoth. Yeah? It looks like it was 60,000 years old. Why? Because the CO2 that it has grown from was about 60,000 years or 100,000 years old. So kind of a fun concept. You can pick corn and say something about fossil fuel emissions. That's the whole idea behind this project. So we've simulated this, first of all, on a relatively fine grid. So now we're not using a global model, we're using a regional model with about a 2-kilometer grid, and we're using seconds time step, and we're really trying to simulate the different emissions from the cities and the roads into this picture. And then we also simulate how corn is growing over the Netherlands, depending on the weather patterns, depending on the time of sowing, depending on the state of the soil. And then this is what we predict are the gradients of this radiocarbon in corn plants that you can pick from all over Europe. And you can see that the really low values, the blue, which means high in fossil fuel, are, of course, in the most industrialized area of Western Europe, which is the Randstad and the Ruhrgebiet. Yeah? And you can see some of these individual spots that will come back later. So you can really see a large area where there is high fossil fuel emissions or low radiocarbon amounts due to the fossil influence on the CO2, 14 CO2 ratio. In addition, you kind of see these hotspots here in red, which is nuclear production of carbon-14. Now, there's a source of carbon-14 which, unfortunately, we have to take into account in Europe, and that is that certain types of nuclear reactors have carbon-14 as a byproduct of the nuclear production process. Also, one of the places where this happens is at the nuclear reprocessing site in Le Hague in France, where they have a very large source of carbon-14 just from reprocessing spent nuclear fuel. So we need to take this into account because this stuff is going to fly over Europe. And so this is part of a research project to separate these two. Okay, this is nice. This was a computer simulation. What about reality? I sent my student out to collect corn samples from all over the Netherlands and all over Europe. We put them on the instrument in Groningen to figure out what are we measuring. So you're now seeing a picture of this atmospheric 14 CO2 field modeled, which are the colorful contours. And you're also seeing that same picture, but now with dots in there. And the dots have the same colors on the scale of carbon-14. And these are the measurements. I hope you can see them from the back, but well, it's actually good if you cannot see them, because it means that the measurement is the same as the model. Yeah? The fact that this is dark blue measured and dark blue model means that we have good correspondence. So also the samples that we are taking are showing these gradients sort of from the greenish colors towards the really intense dark blue, when we were right in the middle of the Ruhrgebiet and going into cleaner areas. Then we went to Paris. Around Paris we took a few samples which are not completely agreeing with the model, but we're still working on this, of course. And we actually, well, I should say she actually drove all the way to Le Hague to figure out if we could find these really high carbon, radiocarbon values near Le Hague. And we did find a few samples, or actually one sample there, we only took 3 I think, that had this really super high carbon-14. So for us, this is sort of an interesting proof, and this is the picture for the Netherlands. Now you see that we're simulating at even higher resolution, because you can see here the emissions from the Maasvlakte. You can see Rotterdam, Amsterdam, Utrecht. You can see a lot of places that are familiar to you probably with high fossil fuel emissions. And also in the Netherlands, we are seeing a very nice progression of these colors across the landscape, just from picking corn and measuring carbon-14. The quantitative estimate of fossil fuels that we want to derive from this is hopefully happening this year. Yeah? So this is really work in progress. I can't show you the total emissions from the Netherlands yet. One interesting side story, yes, I do have time for this, is that big blue spot that we're seeing up there in the Netherlands. And we were saying, like, okay, well, what is this? What sort of company or industrial complex is having these really high fossil fuel emissions? And finally, we figured it out. This is Agrico. This is the potato industry. So why are these emissions over there? Because they reported their emissions, and then with that report, they put in the zip code of the headquarters, which is located right there. So when somebody started to make the fossil fuel emissions map, they said, okay, Agri company has fossil fuel emissions worth of 3 teragrams of carbon, and they are located at this zip code. So that's how this dot happened to be in that map. So it's wrong, yeah? That dot shouldn't be there. It's distributed emissions from all sorts of activity in the potato industry that are going on in the Netherlands, which have all been ascribed to the zip code of the headquarters of the company. Of course, this is one way that you could say, like, so we're independently checking fossil fuel emissions. Well, not really, but it does show that if you take a different view on fossil fuels and how it's reported, that you can find inconsistencies in these kind of products that are important to keep in mind. All right, I told you I'd finish with this last question of how fast are we approaching dangerous levels. I've kind of shown you now that we've learned a lot about the carbon balance, that we have different techniques to learn about the carbon balance. Now we're going into projections. We're going into the future. It's not really my thing, but it's certainly quite interesting to look at. So let's first look at the emissions. Fossil fuel emissions are shown here. They are reported through these dots that are kind of erratic, connected with a thick black line. They are also estimated, or actually they are simulated, based on emission scenarios for IPCC. You can see here these different codes. I think a lot of people are probably a bit familiar with these codes. They represent different scenarios of what we are going to do with our energy infrastructure over the next 50 years. Yeah? And depending on what we do, for instance, A1, F1 is a scenario where we are not doing so much. Yeah, it's basically, we're keeping to the energy infrastructure that we have now, which is mostly fossil fuel based. We'll do some innovation, it'll get cleaner, but there's also a lot more people coming into the world in the next 30 years. So eventually this is going to rise pretty quickly and then level off somewhere in 30 to 50 years. Yeah? Which is a much more pessimistic scenario than, say, the B1 scenario, where we are really investing a lot in alternative energies which are not putting CO2. We're finding ways to store CO2 down in the atmosphere, so we're avoiding emissions as well. Sorry, down in the ground, so we're avoiding emissions as well. And you can see that reality right now is on this A1, F1 track. As a matter of fact, it's a bit above the A1, F1 track. When we had this is the fourth assessment report, the third assessment report, really we can see a big gap within less than 6 years. So with our best knowledge in 2001, we developed scenarios for emissions. 6 years later, we had to do a big revision to the most negative scenario. So right now, we are on a track that is not going to prevent CO2 from going very high. The actual 450 ppm scenario that was talked about by Dr. Boersma before is actually somewhere down here. It's not even on this map, but it's below the B1 scenario. And even the 650 ppm scenario for the future is down here. So we are nowhere near target to meet 450 or 650 ppm. Well, there's a little bit of slack. Luckily, we are also finding, through these methods that we're developing, that the ocean sink is increasing, which is, on one hand, is logical. If you increase the difference of CO2 between the oceans and the land, or the atmosphere and the oceans, sorry, atmosphere being higher than oceans, you pump CO2 into the oceans. We know this pretty well, so a higher difference, because we're emitting into the atmosphere, means a larger sink. And we're seeing that increase in the sink. So that's good, a little bit of extra uptake. We're also seeing an increasing land sink, which is really hard to see because there's so much variability. Yeah? If there's a drought, if there's an El Nino, if there's something happening to our climate, the land biosphere responds very quickly. So I don't really dare to draw a line through this. Yeah? We think there's an increasing land sink, but we can't definitively say there's an upward trend in the sinks of land. But there's good reason to believe that there are increasing land sinks, because first of all, we're reducing the amount of disturbance. Yeah? The land use changes. We are not deforesting as fast anymore as we did in the 80s, basically. Another reason is that plants like CO2. We saw this on my third slide. Plants like CO2. Fertilization effect. Higher CO2 means larger growth of food and crops and trees as well. Then again, we're also seeing that this ocean sink that we thought we understood from first principles, bigger difference means more CO2 into the ocean, is not increasing as efficiently as it should. If we take that model of an increasing difference going into the ocean and slowly making it into the deep ocean, we would see that red line of increasing sinks. But if we now use our best model, either in blue of what the ocean is doing, or the actual observations in the atmosphere, we are seeing that the truth is deviating from this theoretical curve of increasing sink. So the sink is increasing, but not by as much as it should according to what we think we know about the ocean. So that's bad news. Yeah? This ocean sink is not going to keep pace with the increasing emissions. There's also some emerging, well, it's about 5 years old science, but there's a new paper actually out only 2 months ago by Peter Cox et al. There's some new information also about the predicted land sinks. Keep in mind, these are predictions of the land sinks by the climate models that we have good reason to trust for some things, but not for other things. The prediction is that CO2 fertilization is going to make the biosphere happy, and it's going to make the biosphere store lots of extra carbon. Yeah? Lots of extra means not enough to prevent these high CO2 scenarios, but at least not as high as when the land sink would disappear. So CO2 fertilization would help us keep CO2 a little bit low. But if we factor in climate change as well, which is a debatable subject, but certainly we know that if the temperatures are going to increase, we run a risk of more frequency of droughts and disturbance to the biosphere. And we saw before that the biosphere is this thing that can really respond very quickly. Yeah? So if the biosphere is going to respond to climate change, it is not going to store as much carbon as we think, because the droughts are going to kill off trees, which could have had a lifetime of another 30 years of absorbing carbon, but they'll be killed more easily by the droughts that are happening under climate change. Yeah? So the CO2 fertilization effect is possible a good help, but if climate changes too fast, then the biosphere is not a reliable partner for reducing CO2. Second to last slide. So what then is atmospheric CO2 going to be according to the projections? Well, there's some very smooth curves here, so you can see that these are done by climate models with the coarse time step. But what you can certainly see here is that according to different climate models, and there's about 14 different models represented in here, we should be hitting 400 ppm somewhere in the first quarter of this century. Well, we did. 2013, we hit 400 ppm. Not really officially, but we'll hit it in a few months for sure. You can also see that 500 ppm, and I'm sort of taking the middle range of all these models now, we are going to hit before 2050. Yeah? It's only going to take another 30 years to add another 100 ppm. So that means that the growth rate is going to accelerate of CO2 in the atmosphere. As a matter of fact, most of us will probably see 500 ppm of CO2. And maybe think back about this talk, when you saw 400 ppm CO2 30 years ago. If we're lucky, it might be 20 years or 40 years. Well, we'll see. Anyway, in about 30 years, we'll see 500 ppm. You can see that the next 100 ppm is going to be added even faster. Yeah? And the final 100 ppm is going to be only in about 10 years. So the intervals by which we're seeing this increase in CO2 are predicted to go to become shorter and shorter pretty quickly. What is dangerous at this level? It's really hard to tell. The science is being made as we speak. We know from first principles that this is going to incur a very large greenhouse forcing with probable climate change, but greenhouse forcing for sure, physical principle, very easy to understand, and it's going to wreak havoc on the surface oceans, because the chemistry effect of CO2 going into a shallow pool of water, we know pretty well as well. How dangerous is that? We'll see. We're the Netherlands. We can innovate. We have technology. We will live without the fish. Yeah? We can say that dangerous for the Netherlands means something else than dangerous for Bangladesh. But I'm not going into that political discussion. Dangerous, we'll see. That finishes most of the content of the presentation that I had prepared for you. I had promised in my abstract as well to argue a little bit about why monitoring is overdue. To see if we can get back in time, though, I'll just leave these talking points up here for us to maybe discuss at this point. So I thank you for your attention.